Nuclear power is a high-yield, clean energy solution, but the global market is built on a bottleneck. Traditional reactors require uranium, a fuel source concentrated in the hands of a few nations. India currently generates about 3% of its electricity from nuclear energy. To meet its rising demands, the government plans to multiply that output 12 times over within the next decade, but the geology is against them. India holds between 1 and 2% of the world's uranium reserves, leaving them far behind the major nuclear powers. This scarcity creates a geopolitical risk. We see the impact of this leverage in the United States' focus on Iran's enrichment programs, where control over nuclear fuel often dictates national sovereignty. If India continues to build traditional reactors, they will merely replace a dependency on foreign fossil fuels with a dependency on foreign uranium. However, India possesses a different radioactive resource in abundance. 25% of the world's thorium is found within India's monazite sands. The problem is that thorium is relatively inert. Unlike uranium, you cannot load it into a standard reactor and generate power directly. Decades ago, Dr. Homi Bhabha designed a 3-stage master plan to bypass the uranium shortage. His strategy was to use early-stage reactors to create the specific conditions needed to eventually burn thorium. While India has operated in Stage 1 for years, this recent breakthrough marks the country's transition into the second phase of that blueprint. This transition is centered at the Kalpakkam facility, home to the 500-megawatt prototype Fast Breeder Reactor. In a typical reactor, fuel is consumed to produce heat, which boils water to spin a turbine. A breeder reactor is different. It uses high-energy neutrons to produce more fissile material than it actually consumes during operation. This design allows the facility to simultaneously generate electricity for the grid and manufacture a constant supply of its own reactor fuel. The process begins with uranium-238. Inside the core, a fast-moving neutron collides with the uranium nucleus. This triggers beta decay, where the element morphs into plutonium. Engineers then apply this same bombardment technique to India's inert thorium-232. As the thorium absorbs neutrons, it briefly becomes protactinium before stabilizing as uranium-233, a highly reactive isotope that can be used as fuel. Managing this requires maintaining criticality, a state where the nuclear chain reaction is perfectly balanced to provide steady power without becoming uncontrolled. By mastering this cycle, India has demonstrated the ability to convert raw thorium into usable energy in a self-sustaining commercial loop. Reaching this milestone is a feat most global powers have failed to achieve. Despite the potential, many Western nations eventually abandoned the fast breeder cycle. The financial cost of these failures was enormous. The US invested $15 billion, Japan $12 billion, and the UK $8 billion before ending their commercial programs. India reached this stage for less than $1 billion. This efficiency was driven by 22 years of domestic development, utilizing over 200 Indian small and medium businesses to manufacture the reactor's complex components. It shows that long-term engineering persistence can solve technical hurdles that large-scale capital alone could not. Establishing Stage 2 provides the plutonium supply necessary to begin Stage 3, the operation of reactors running primarily on thorium-transformed fuel. This puts India on a path toward energy independence, where its power grid is no longer vulnerable to fluctuations in the global uranium supply. The International Atomic Energy Agency has noted this progress, highlighting the technical sophistication required to manage this nuclear cycle. By utilizing the thorium in its own soil, India has overcome its natural uranium deficit, creating a domestic foundation for its own clean energy future.